Hello everyone. So in this video, we will understand what is interpolation and then what are the Newton's forward and Newton's backward interpolation formulas. So let's first understand about interpolation. So suppose you have given some values of function y equal to fx, which is a polynomial, and this polynomial is given at n plus 1 number of data points. So it is given at n plus 1 number of data points. So let's write these values at given particular points. So here I have xi's and then y equal to f of xi's here. And these observations are x0, x1, x2, x3, and so on, xn. Y values are y0, y1, y2, y3, and so on, yn. So what does interpolation is? It actually computes the values in between the range of given values. So like here, x0 is the initial value and xn is the final x value. So if I want to estimate y at any xm, which is equal to f of xm, where x0 less or equal to xm less or equal to xn. Then the interpolation comes into the picture. That means we are finding certain values, function values at xm, and we need the functional value at this particular point. So this is actually the problem of interpolation. So in one sentence, if I want to define what is interpolation, so finding the unknown values within the given range of data set. Given range of data set, which is known. So known data point. This is exactly the interpolation. Another word is similar to that. So basically here interpolation means you are finding the value inside the data point. Like here you are finding for xm. And there is a similar word extrapolation, which means you are finding the value outside the data point, which we will not talk here. So we will consider only here the interpolation, which means estimating the unknown value within the given range of known data points. Now, for example, it's very easy to understand. Suppose we have given certain temperatures at particular times. So we have time here, you can say in the, and we have temperature. So let's say it is known that at 2 p.m. what is temperature? Let's say 30, and at 4 p.m. let's say it's 40, and it's in degree centigrade. And if it is at 6 p.m. let's say it's 60. And now if you want to compute or you want to estimate temperature at certain mid times at, let's say, 3 p.m. So this particular problem is a problem of interpolation, because here the xm is now at 3 p.m. and you are finding the temperature. So this is the exactly the problem of interpolation. So let us now move forward and see what are the two best interpolation formulas. So first one is here Newton's Farward formula, and here this particular formula is used when data is equally spaced. This means the gap between xi plus 1 minus xi is same for each I. That means if I see here the range here, so difference between this data and the difference between this data, difference between these two points is equal. So this Newton's forward and Newton's backward formulas are applicable when the data point is equally spaced. It's very important point here. And this particular use to estimate the value at the beginning of the data points. This means the xm should be at the beginning of the data set. Then we go for forward formula, and it uses forward difference operator. We generally call it del, where del yi is defined as yi plus 1 minus yi. So that means next y value minus current y value is delta y at current. So let us see the exact formula. So this is the formula. So we are approximating a polynomial based on the data set. So y equal to fx equal to y0. So which is initial y value plus p delta y plus p into p minus 1 by 2 factorial delta y0 plus p into p minus 1 into p minus 2 delta q y0 plus p into p minus 1 p minus 2 p minus 3 divided by 4 factorial into delta 4 y naught plus and so on. So the number of terms will depends on how many data points are given. And here, very important, what is the x naught? The initial data point. And what is y naught? Initial y value. And the variable p here is x minus x naught upon h. So in some textbooks, it is taken as p is taken as u or v. So that's your choice. Here I am denoting it by p. So p equal to x means the required value I have taken as m xm. So at which point you want the value of function, that value minus the initial value divided by step size. Step size will be same for between the data points. So the gap between two data sets, which is equal for every two points. So this is Newton's forward formula. Now let's see how to compute these differences. So we have a Newton forward difference table. So in this table, you can see here, we have the x values and then we have y values. And I have written up to this n equal to 4. So here you can write n, and this is n equal to 0 here, 1 here, 2 here, 3 here. So what is the forward difference here? First difference is delta of y0, which is as I written here, the next value minus current value. So delta y0 is y1 means next value minus present value, the current value, so y0. Similarly, delta y1 will be next value means y2. So difference between these two is indicated by this, and difference between these two is indicated by this. So this is the difference here. First forward difference, and delta y2 equal to y3 minus y2. And now if I go for second difference, so del square y0, again apply the definition here. So del square y0 means delta y1 minus del of y0. So you compute difference between these two, and then this delta square y1 is difference between these two. Now we have del square y0 and del square y1 in this column. So third difference will be the difference between these two points, which is delta q y0. So this is the Newton's forward difference table. And for forward values, we will consider the initial value in the formula, the initial y value in the formula, and then first forward difference, and then the second forward difference, and then third forward difference, and if number of terms are more, then fourth forward difference. So from Newton difference table, we can easily see that in this formula, the values y0, delta y0, delta square y0, sorry, mistake, and delta q y0, and so on, delta 4 y0. These all values will be calculated from the top row of the table. So top row means the first entries in the table. This is very important to note down. Now let's see what is the backward difference interpolation formula. So here it is again stating that it is used for equally spaced data points, and it uses when you want the value near the end of the data points. That's why the name is backward formula. And it uses the backward difference operator, which is defined as nebula of yi equal to current value minus previous value. So as it defines the current value minus previous, so it cannot start from the beginning, because beginning I have the current value, then I have no previous value. So in the difference table, you can easily understand the values will be taken from the bottom row. Now let's first see the formula here. So it has approximated as yn, that means the last value, plus delta yn, sorry, the nebula is square yn, and then nebula cube yn, and in place of p minus 1 here, we have p plus 1, and then p plus 2. So the sign is changed here. And if you see, the xn means last x value, yn means last y value, and p is defined as x minus xn, because backward we are using when this required value is near the end of the data point. So we are taking the difference of this required value minus the last value, so that the p should be smaller, and it will save the time in computation divided by step size. Okay, so this is about Newton's backward formula. And here you can see, I will go again to the table here. Now in this you need to understand, although we'll discuss this in coming example here. So while using backward, in this case, this is your last y value xn, and this is your last y value yn. And if you consider here, this is the first difference that we call nebula y. So this value I will take as the backward differences. And similarly, this value will be used as backward, and finally this value will be used as backward. So if you see here, values in the table will not change, only the pattern in which we are taking here is changed. So because backward starts from the backward side, so we will make the values from the last of the row. So we are taking last of the row from the table. So let us now see one example here. So example is, suppose the electrical engineering is analyzing the output response of nonlinear system, and the system output is measured at equal input intervals as shown here as input. So it has 1, 2, 3, 4. So you can see here it is equally spaced data. Equally spaced data. So I can use Newton forward, I can use Newton backward. And the Y values are given as 1, A, 27 and 64. And it is stating that since continuous measurement is not possible, the engineers need to estimate output values at intermediate points. That means you have to use the interpolation technique. So task to do are, we have to compute the output as x equal to 2.5 and output at x equal to 3.5. So how to compute it? Because x equal to 2.5 is near about the first value. So we will go with forward formula, and x equal to 3.5 is at the last. So we'll go with backward formula. So let's make the table first here. Data points are 1, 2, 3, 4. So let's make the table here first. So Newton's table. So I need to capture the data points here. So x is value given, y equal to fx given, so 1, 2, 3 and 4. And these points are given as 1, 8, 27 and 64. Now I will make the difference here first, delta y. Then I have delta square y. Then I have delta cube y. So delta y is forward difference. So next value means 8 minus previous value 1. So I have difference is now here 7. And the next value is 27 minus this previous value. So it has 27 minus 8, which is 19. And then 64 minus 27, which is 37. So this is the first forward. Now in the second difference, I will compute the difference between these two. Uh, so I have 19 minus 7 is 12 here, and 37 minus 19, which is 18 here. So this is the second difference. Now for third difference, I will take difference between these two. So 18 minus 12 is 6. Now this is the difference table, and the same table can be used for forward formula and can use for the backward. So depending on the value required, we will use backward or forward. So in the first one, we have to compute the value. We have to estimate the value at xm equal to 2.5 and xm equal to 3.5. So let's go for 2.5 and see what the formula gives. So we have here initial point, x0 equal to 1. What is initial y value? y0 equal to 1 here again. And what is the p value here? So the p value is x minus x0, because we are using forward formula at this point is nearby the beginning, divided by h, which is step size. So step size means the difference between x values. So I have 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. So difference between each data point is equal and it is 1. So this will now be changed as 2.5, that means the required value, minus the initial value, that is 1, and then a step size 1. So this is now is 1.5. Now I can write the formula and put the values. So the formula here is y equal to fx, and it is approximated as y0 plus p and delta y plus p into p minus 1 divided by 2 factorial and delta square y 0. Okay, y0 plus p into p minus 1 and p minus 2 divided by 3 factorial into delta q y0. So because we have difference till third, so we are writing the formula till third. Now just put the values here. So in this we have initial value as y0 is 1 plus this p value is 1.5 into delta y is, you can see the table here, delta y0 is the first value and delta square y0, let's highlight with y square is 12 and third is 6 and initial value is 1. So top row is used here. So let's put these values there. So into we have 7 and plus 1.5 into 1.5 minus 1. So 0.5 divided by 2 factorial, which is 2 exactly, and into second difference is 12 here and plus 1.5, then 0.5 and then 1.5 minus 2, so minus 0.5 and divide by 3 factorial is 3 into 2 into 1, so it is 6, and into I have third difference which is 6. So now if I compute here, I will get these values as 1 plus this 10.5 and plus 4.5 minus, because there is negative sign here, so minus 0.375, and overall I got here 15.625. So this is your y at 2.5, and here it should be the y at 3, oh sorry, 2.5. So this value should be x here. P is used as particular value here. So P is not now a number here. So we got this particular value here. Now for computing at x equal to 3.5, I will use backward formula. And by using that, what is the change here? So for x equal to 3.5, we use Newton backward. So here, what are the requirements? What is the xn? Xn means last value equal to, and what is yn, and then p. So let's see what in the table, what is last value. So I have here, this is your x0, this is x1, this is x2, this is x3. Okay. So last value is x3 here equal to 4, and last value is y3 here, which is 64, and p value is x minus last value, that means x3 divided by h, which is step size. So this is now changed as, because this x required is 3.5, so I will put 3.5 minus last value, that is 4, and divide by 1. So it came as minus 0.5. So your p value is minus 0.5. Now let us write the formula, which is Newton's backward formula. So y is approximated as yn plus p, and backward operator of yn plus p into, in previous formula it was p plus 1, here it is p plus 1, in previous it was p minus 1. So p plus 1 divided by 2 factorial into, so here 2 factorial into second backward difference and plus p into p plus 1 and p plus 2 divided by 3 factorial and third backward difference. Because we have difference till 3, so we are writing the formula till third term, the third difference actually. And now let's put the values. So I have now yn is 64 and plus minus 0.5 into the first backward difference here, and now second backward difference here, and third backward difference. Now you can look at the table here. So in the table, as I said, we have to go for last or the bottom row. So I have the x4 here, and sorry, x3 here as 4 and yn as 64. First backward difference is this one, second backward difference is this one, and third backward difference is this one. So let's put these values in the formula. So I will get here into 37 and plus here minus 0.5 into minus 0.5 plus 1. So I have here 0.5 and divide by 2 factorial, which is 2 exactly, into the second difference, which is 18, and plus minus 0.5 into 0.5, and minus 0.5 plus 2 is 1.5, and divide by 3 factorial, which is 6 into 6. So this will came as 64 and minus 18.5 and plus, not plus here, minus again because negative sign here. So minus here, this will be 2.25 and then minus 0.375. So this value will come as 42.87. So this is your y at 3.5. So you have estimated two values using interpolation formulas. Now, very interesting point is here, why we are using backward and forward formulas to estimate the values at in intermediate points. This is because if I use forward formula, then the computation will be easier if value is nearby the beginning, and I use backward formula if value is at the end of the data point, and it will save the computation time. So by using the similar approach, you can compute this next problem. So here data point is again given as equally spaced and values are given. So now using appropriate interpolation method, either forward or backward, estimate the stock price on the day 3.7 and 1.2. So generally 1.2 lies near the beginning, so we have to use here forward, and 3.7 lying at the end, so we have to use for this backward. So I hope you understand the Newton forward and Newton backward interpolation formulas, and you apply the concept in this particular problem, and you will solve this by yourself. So this is all in this particular video. In the next video, I will discuss about Lagrange interpolation formula. And then I will summarize also the key points and the basic difference between all these interpolations.